Okay, so we're back. Welcome back to Econometrics B, still about multinomial responses. Now we have, we have made sure that parameters are appropriately identified. We've estimated the model. Now let's look at what we can use the model for and how we interpret the results. Okay, coefficients usually, especially in the multinomial logit model, can be hard to interpret. I mean, we talk about the conditional logit model that the coefficients there would be interpreted as, say, the marginal utility. Okay, the marginal utility, and that would be like comparable across a different attributes. So maybe you get higher marginal utility of, say, the age of a car, or compared to the size of the car. Okay, that these things are comparable across the different variables. Okay, in some sense, you can also do the same type of comparison. It's across different variables. Which variables are more important? But then they may be scaled very differently, and maybe we'll want to actually calculate things that are easier to understand. The obvious starting point is the marginal effects, especially in the multinomial logit. It's really hard to understand the coefficients beta directly. So we want to calculate marginal effects. So in the conditional logit, well, here the marginal effects with respect to a change in a alternative specific covariate, that's what you get when you differentiate the response probability with respect to that. And now I'm considering a continuous change. You guys, of course, know how to calculate a discrete change. Well, you calculate the response probability for one value, and then you calculate the probability for the other value. You take the difference, and then that's the effect of changing, say, some variable from 0 to 1. Okay, or you can change many variables and make counterfactual changes and whatnot. But we're looking at like our marginal change in a continuous variable. Like, what happens if I change the price of the good, for example. So what you get is that this is the probability of choosing the good times 1 minus the probability times beta. Okay. 1 only happens if basically the variable I'm differentiating with respect to is also an attribute of the probability for the alternative under consideration. So J. Okay, so it's K is equal to J. Otherwise, this is going to be 0, and then you got negative basically the two probabilities multiplied together or squared. Okay, because it's the same probability if K is equal to if K is equal to J. Okay? These are the marginal effects, and it's clear that these marginal effects is determined by the sign of beta. Okay, because these probabilities here, well, they are always positive. This guy here is always positive if we're looking at like a cross derivative, like if you change the price of the price of car number, the price of BMW. What's the probability that what is the change in the probability of choosing a Fiat? Okay. In that case, that probability, this is always positive. And it's also positive if you're looking at the same, changing the same attributes of the probability you're considering, or the alternative you're considering. Okay, so this is positive. So these effects are essentially determined by the size of beta. Then it's with the opposite sign if we are looking at the own price at the same alternative. Okay. So you can we're going to work it out. The bottom line is you can determine the sign from looking at the coefficient. Okay, looking at the coefficient. Whereas with the multinomial logit, it's not enough to look at one coefficient, because there is more than one coefficient for one alternative. There's one for each alternative. Okay, and so what you get here is really the probability times beta minus the probability weighted sum over all the alternatives. Okay, so this means, unlike in the binary response model, where you could determine the sign of the partial effect solely from the sign of beta. Well, we cannot do that here because once there's multiple alternatives, you don't know what those probabilities are. Well, it depends on the probabilities and the signs of all these other factors. Okay, so this makes the betas extremely hard to interpret themselves in the multinomial logit model, particularly, which is why we want to calculate these partial effects and do it because it's not that hard, right? And by the way, if you have a more general, here I've assumed a linear index like we would have in the conditional logit model. If that's not the case, this would just be the derivative of the utility with respect to x, okay? With respect to x, xik, okay? And down here, it's the same thing, but here would be, you would need to calculate all the different derivatives across all the different alternatives and then make this weighting, okay? Anyway, these things are formulas. You can calculate it, so it's not a big deal. It's just don't tempt yourself to only try to focus on understanding coefficients in multinomial logit model. If you calculate these effects, well, you need to calculate standard errors of them, and you don't get that directly out of your estimation routine by calculating, the diagonal elements of the inverse of the Hessian or the sandwich, the variance covariance matrix implied by the sandwich formula. You would have to use the delta method, and that's an exercise in actually doing that in the coming exercises where you would have to do that. You could also do Bootstrap. It's described in chapter 12 in Woolrich, and there's many ways of doing Bootstrap. I would say the very hand-waving and pragmatic version of what Bootstrap is that you draw from the sample. Okay, so you have a sample of observations, you draw from the sample. You take a draw of the size n with replacement. So it means that some observations can be there several times. You draw from the sample with replacement, and then you estimate a model. That's your Bootstrap estimate. Okay, now you got one estimate. Okay, now then you do it again. You draw from the sample with replacement of sample of size n, and then you get another estimate. These are not the same because they are not the same sample, right? And then you do it again and again and again. Let's say you take like 500 Bootstrap samples and estimate the model 500 times. Then the distribution of those estimates is an approximation of the distribution of the estimator. And so you can calculate the standard errors, the Bootstrap standard errors, as the standard deviation in that distribution. And for each of these Bootstrap estimates, right, the parameter estimates, you can also calculate the implied or average partial effects. Okay, so you get like, if you have 500 estimates, you got also 500 partial effects. Then you take that distribution again, that's your Bootstrap distribution of the partial effects, and then you calculate the standard deviation, that's your standard errors on the marginal effects, okay? Average partial effects. So there's several, and that applies to any statistic that you want to calculate. Based on that, you can calculate them using the Bootstrap. Okay, that's described in chapter 12. I'm not sure we're doing that, but it's good to know that there are other ways than the delta method. Of course, it's more computational intensive to estimate the model 500 times, but once you know the parameter estimates, you already got really good starting values, so you just use those again. Another thing to say about the marginal effects is that since the probabilities across alternatives always sum to 1, marginal effects should sum up to 0. If they're not, you have a bug. Okay, so that's a good check. Then another thing, if you want to think about demand for consumer goods, for example, or in estimating a demand model, then, for example, the average twice probabilities, that would actually represent the market shares. Okay, so here's the market shares. That would be like the average people that choose a particular good, right? And if you let n go to infinity, well, that actually converges to the probability of choosing that alternative. Okay, so average marginal effects, they then measure how those market shares changes. Okay, so that's just it's nice to put a little bit of economics and meaning into what you're doing, and that's actually what we're trying to do here. Okay, so let's talk a little bit about the parameter interpretation. I already alluded to that we really have to be cautious when in interpreting the parameters in the multinomial logit, because it's such a complicated function of all the parameters across the different alternatives. The sign of the marginal effects is not determined by beta alone. Instead, you could, for example, consider the log-odds ratio with respect to some normalized alternative. That's the log of the relative size of say, alternative J relative to, say, alternative 1 or alternative 0. Then you take the log of the two probabilities, and then you see here, this guy here drops out, right? It's the same denominator. And then difference in exponentials, well, it's just the difference on yeah, well, anyway, it collapses to this once you take the log. If this guy here is, for example, normalized to 0. Okay, I apologize for not making this benchmark alternative 0, but I guess I changed notation on the run. Anyway, so it measures this log-odds ratio relative to some benchmark alternative, measures the change in the relative risk when X changes by 1 unit. Okay, so I don't know. I mean, to me, it's not super intuitive. Other people are smarter than me, but at least that's what it means. I think it's easier to think of or interpret the marginal effect. The marginal effects. How much does it how much does the market shares actually change when I change an attribute of all the different alternatives? I think that's more intuitive, or even the elasticities we're going to look at in a second. This is the type of stuff that's coming out of standard softwares often. Like, this is why they often, when you have linear and X utility like we have here, this is why they often report the log, software report the log-odds ratios. Okay, so why don't we take an example of this? So we're replicating that now the results of table 16.1 in Woolrich's textbook. It's on page 645. It's called the School and Employment Decision of Young Men, and the data set is based on the subset of the data set that was used to estimate a career choice model. It's actually one of my favorite paper by Mike Keane and Ken Mulpin in Journal of Political Economy in 1997. Really worth reading, like an occupational choice dynamic programming model. It's called the Career Decision of Young Men, but that's a dynamic model. So we're doing just a reduced form or a small version of that. That's what Woolrich is doing. But that's where that data is originally coming from. Anyway, so why don't we try to, Keen is not defined. I'm gonna pause it. I haven't put it into the right folder, so I haven't put the data there. Just a second, I'm gonna pause and be back. Okay, so I'm back. Now I kind of, I found the bug. That's what happens when you're using Python notebooks and everything is still in memory. You don't, run the program from the top. So it's like an illustration of bad, programming habits, right? So what happened was I renamed the variable. Basically, I renamed the variable Keen, the name of the data set, from Keen to DF. And then I forgot that I do it everywhere, but then Keen was still, this original variable was still in the memory, and then everything was working out beautifully. And so now it should work, okay? So now I've read in the data set Keen into this data frame here. I select only the data from year 9087, and then there's some missing values in this variable status, which is a discrete response for multinomial response for employment status, 0 for a school, 1 for home, and 2 for work. So I want to drop any missing observations, or drop NA. That's like dropping the missing observations for any of the variables that I'm using. and if I do so, well, I get the same data set that was used to estimate the parameters in Woolridge's textbook. And then we have four explanatory variables with education, with experience squared, and then we have this black dummy. And then we have status, that's the dependent variable that takes the three different outcomes, two for working, and so like 1,286 people were working, and then one for home, 332 of them, and then zero for school, so about 100 people were in school in this data set. I think the data set is well, you could try to estimate this for different years and see if parameters are changing. The point I want to make here was mostly about parameter interpretation, not so much about this particular model here. Anyway, what we do is we estimate a multinomial logit model, and I'm using the MNL Logit from the stats models library that I've read in here. The stats models, that's very nice. I mean, it's some canned routine there, like linear regression and you know, Poisson regressions and various you know, logit models and propet models and so on. Like, you know, standard routines that are just nice to have. So I didn't spend the time to code up this, but you're going to do that in the exercises and see. So here I'm cheating a little bit, and you know, just let other people do the work. So here we basically define the model object, and then ask it to fit it, and then we'll present the results. And here the results are. And you can actually compare these results to the textbook. They should add up. So what are we getting here? I mean, first of all, the status, the outcome variable school, that's the alternative that we leave out. So we normalize the coefficients against that alternative, which means that if you look at it, there's only a set of coefficients for alternative 1 and alternative 2, which is home and work. Okay. Now, so you look at a particular coefficient here, it's negative. So education is negative. So the more in principle, then you would think, well, if I just look at this coefficient, if that does that mean that I'm less likely to stay at home if I get more education? Well, well, you're even less likely to well. So this is hard to interpret, right? So you know, there was this probability weighting across the different alternatives, and what about the other one? It's really compared to school, right? So it means I'm less likely to compare to school. No, we just decided we cannot do this, okay? So what you can learn from these estimates is how does the log odds ratio between schooling, which is the outside alternative, and staying at home changes. Well, that's negative, okay? So why don't we move on and calculate those partial effects and do that, okay? So I've also prepared that in the oven. And here you see suddenly, now you get a partial effect for each of the different alternatives, right? And here you see that the education, well, that increases probability of staying in school. Education decreases the probability of staying at home and being at the labor market. Now, this is more interpretable, right? This is it's not like you have to compare many different parameters. We also get standard errors on these, and I think they're computed using the delta method. Okay, so that's kind of an example of an output of a multinomial logit model. I actually have. Do I have some? I think I have an example of yeah, I have an example here of a paper that's doing a conditional logit model. It's actually not a conditional logit model. It's a nested logit model, but let's just not focus about that. It's a really nice paper about car sales and used car stocks in the automobile market by Jim Berkovich. It came in RAND in 1985, so it's kind of a classic, actually. It's really one of the first papers of modeling automobiles that was allowing for equilibrium effects and scrappage and all sorts of things. But that's not what we want to talk about today. What I want to talk about here is just to give an example here of, let's find the empirical results. Here's some different these are consumers making choices between different types of cars. So here's this like 13 different types of cars. And then the cars are also, they also come in different vintages for different years. Okay, so different ages of cars. And so there's 10 different years, and then there's a category for being old. So this gives like 10 different model years times 13, that's 130. And then there's just a category for very old cars. So that's 131 alternatives. And so if you look at the table or with the coefficients, it's not like you will not find 131 coefficients for each explanatory variable. So here are the variables, and down here you see the coefficients. Okay, I'm not going to spend a lot of time doing. You can read the paper yourself. It's a very good paper. But what you see here, there's essentially just one coefficient for each alternative. These are just different specifications for different splits of the sample. Those that have one car, those are two cars, or three cars. Don't worry about that. This is one logit estimation, or nested logit estimation. And then you see, here's a coefficient on, say, the OP cost. We can see up here, what is that? That's the operating cost of vehicle in cents per mile. So this is like the local gas price divided by the miles per gallon. So this is like the fuel efficiency of the car. So this means that if it's a very, the car has very good fuel economy, then that price is going to be low. Okay, so maybe consumers, they worry about how expensive it is to drive the car. So that's a variable to include, and then you let that vary across the different alternatives, right? So that, the different types of cars that we had in the sample, where are they? So they're right here. All these different cars, a Jeep and say a Toyota Corolla may have very different fuel efficiencies and very different other attributes. And these are the things you can control for by including all these different attributes into the estimation of your model. Now, don't worry so much about this and being a nested logit for now. I mean, we'll talk about that next time. But the key thing here, what is the same, is that there's variables that varies across the alternatives, and the coefficients are not. Okay, and you can estimate the coefficients has a meaning here, namely the marginal utility of changing that variable. So the marginal utility up to scale and up to a constant is affected by the operating cost in a negative way. Okay, which is kind of intuitive. You don't like to pay a lot of money of driving your car. Okay, let's look at other attributes. That's the age of the car, also negative, right? So you don't like to drive old clunkers. Okay, and then there's like specific attributes for some cars that you may want to have, like some alternative specific constants or some constants for some certain groups of vehicles to account for that. So that's like here's a capital cost. It's kind of instead of including it in a as a linear function, they just included in different segments. So it's like divided into different categories. But you can see people essentially don't like to pay a lot of money from the car. So they're operating like, we like consumers to operate. Okay, they don't like to pay money. They like to enjoy goods. So that's kind of an example. And you can see here the difference here to our example with the multinomial logit is really clear. Here you get like a set of estimates for each alternative. Had we had that for a Berkovich paper, we would have had like 131 coefficients for each of the alternatives. So you can see also why in high dimensional choice modeling, you can easily end up with like lots of parameters. So if your model, say, for example, so the residential and work location choices between different regions of Denmark, like it's just 100 by 100. So then you get like 10,000 categories. That's 10,000 coefficients for each of the alternatives. Okay, unless of course you make parameter restrictions that some are the same. Okay, so this could become highly computationally advantage demanding. Okay, and that's so in those situations, well, you better actually limit the number of explanatory variables, or have a very good optimizer and a good computer. A few more things I want to move on from here. Talk about a little bit about additional features of interest that we might want to calculate. I mean, this is what I'm trying to say here. Why spend so much time estimating models if you're not using them for anything else than from from just looking at coefficients you don't understand, right? So that's why we calculate marginal effects, right? That's why we want to interpret coefficients and give them meaning. But there's more to it here, especially when you're written up a full framework for utility maximization. You can calculate the welfare of the consumers, right? You know what in principle, up to scale and up to some constant, what is the utility or the maximal attainable utility for the consumers? We can calculate that. Same with the marginal utility of money. Well, if there's something that is money metric in there, well, you can potentially estimate that and learn about the effects of the marginal utilities of other goods in monetary terms instead of utility terms. So you can calculate the willingness to pay and calculate money metric consumer, or in a firm context, producer surpluses, an own price and cross price elasticities. This is what we, and use the model for calculating counterfactuals of various changes in the explanatory variables. So let's talk a little bit about that. I mean, this is really the top of the iceberg, but you could use economic models for so many things. Okay, so here's the maximal expected utility, the log sum. Okay, so the maximal attainable utility for a consumer, well, that's the max of the utility, right? Which is basically the max of V plus epsilon. Okay, so this we cannot really compute, right? Because we don't know what epsilon is, right? So I mean, unless you know epsilon, you can't compute that. But what you can compute is we can calculate the expected value. So taking the expectation with respect to that epsilon, and so to say, integrate it out like with Thea. Okay, so it's like the expectation of the maximal welfare, where we have kind of taken the expectation over the distribution of all those epsilons. Now I'm not going to spend like another page of algebra to show you that this formula holds, but this is the like this j-dimensional integral over that distribution. It also reduces to something nice. Okay, and this is often called the Emax operator, or the social surplus function, or the log sum in the Logit formula. This is called, and this is what measures kind of the maximal expected utility, where you take the expectation with respect to that distribution of epsilons. Okay, so this is a good welfare measure. Okay, so this is a measure for how well consumers off. And we can calculate it in the Logit model. We can calculate it in closed form. And now, you guys, you may have seen what is this? Well, this is what is inside here is actual denominator of the probability. And there's another nice feature of this. If you differentiate this guy with respect to V, well, then you get 1 over this guy times the inner derivative. That's the exponential for that alternative that you're differentiating with respect to. So you got the Logit formula. That's a derivative of this guy here. Okay, that's a response probability. It makes sense, right? That the response probability is somehow increasing in how much your expected welfare is increasing as you change those explanatory variables. Okay, so this is this result is actually more general. It applies also to more general forms. It's not only about the log sum that you get the derivatives at the derivatives of this guy. That's going to be the response probabilities also in more general formulations. I know we can't really differentiate the max operator is non-differentiable, at least at one point, right? But it is really, the derivative is the indicator function in some sense, and then you take the expectation of the indicator function, you got your probabilities. Beautiful, beautiful. Okay, we call sometimes this also the log sum, or the the smooth max operator. And if you rewrite a little bit, you will see, if you sit down with pencil paper, you can see if you can subtract any number in here, you can just add it outside. So let's just scale utility a little bit here again. So you scale up the epsilon. In that case, the expected max, where you have an epsilon inside, looks like this. Okay, so then you just essentially multiply with sigma and divide by sigma inside. Now we can rewrite this by subtracting any number, any fixed number, say alpha, and then you would have alpha plus what is here minus that alpha, and said this is what we had done here, and then what I've subtracted is one particular number, and then the max overall alternatives. Okay, so and this is valid. Okay, now if you look at what you have here, since this is the max, it's always greater than this guy here, and this means that what you have in bracket here is negative. So if you scale this, this is negative, and then you divide by sigma. So if the sigma goes to 0, this means that this go to really big negative, minus infinity. And what is the expected value of minus infinity? That is 0. So this is, in other words, converging to 0 as the as sigma is going to infinity. I know it's multiplied by sigma, but you know what exponentials are doing, so they're falling very fast. Okay, so this means that as sigma scale down that utility, or that unobserved component of utility, well, it's like it's also disappearing, right? And then you don't have to take max over anything, and then you're left with the max. Okay, so that's one thing. That's why we call it kind of the smooth max operator in some sense. I'm going to show you a picture here. Here's this max operator, the max of 2. You can't really see what's going on, but it's like the max of 2 variables. So why that I'm plotted, and then 0. So you got 0 here. So there. And then you can see basically that this is not a smooth function. It's really have the kinks wherever you turn from one being the max to the next being the max, but otherwise it's just the 45-degree line in the direction you're considering. Okay, and down here you got the smooth max operator, and you see that it has the same shape, and then as sigma would go to 0, then they're going to be more and more alike and less smooth. That's why we call it the smooth max operator. What else? What else is to say? Another thing I want to say here is, as you can see, this effect here, this last effect that makes it not the max, is going to be increasing in the number of alternatives. This is always positive, so it's always positive, this part. And the more terms that there are, the more positive parts are. And you think about the intuition of this. It is like if you get more opportunities for getting extreme value shocks that you don't have to accept, because you could just choose another alternative that has a higher extreme value shock. On average, it's going to increase your expected utility. So that gives consumers consumers have a lot of variety in some sense. The more alternatives, the higher the chance that for idiosyncratic reasons get a good utility shock. Okay, so this I mean, sometimes you need to bear that in mind when you interpret models, especially with high levels of with many alternatives. Okay, let's see if we are back. Okay, now we also want to. I'm screwing up the equations here. Maybe I should just zoom out a little bit. Okay, so this I hope you can see this. Okay. Why is it not going to the next line? Anyway. So here's the monometric. What you can do here is that we want to express these matters in monetary terms sometimes, and sometimes that's feasible. Okay, of course, in order to say something about money, there needs to be something in the model that has something to do with money, like prices or income or things that varies, that has money metric values, right? Okay. So income, that would cancel out of the multinomial, the conditional logit model, because it doesn't vary across alternatives, unless of course that income is something that's related to different alternatives. Maybe you could higher income if you take a particular job compared to another job, right? In that case, you could use the income. It's money metric. It's measured in dollars or kroner or euros or whatever. Okay. So here's an example, just a model where you have the following specification of utility. Utility is some coefficient times the price of the good plus delta times the price from some attributes of that delta set times some attribute from alternative J. By the way, there's a typo here. I'll put a J here again, okay? And then PJ, that's the price of that good, and set J, that's some other attribute. So let's, in the car example, it could be like the size of the car, or the color of the car, or other attributes of the car. Okay, now the price response, Well, the delta, the coefficient here, that would be the response, that would be the marginal utility of money. We already talked about that, right? But then we can use this price parameter to recompute things in money metric terms by translating welfare that's measured in utility units into monetary units. Okay, so we essentially just divide through with that coefficient, which makes that unit of utility disappear. Now I've added a little constant here, and I do that because to remind ourselves that utility does not really have, we haven't identified the level of that utility, right? So this means that this essentially means that the expected value of this consumer surplus, well, you know, you can scale that up and down as much as you want by simply just, you know, adding, making a normalization by adding a constant to your utility function. It would scale up and down that. But usually we are not interested in the expected value of the consumer surplus per se. It doesn't have any economic meaning. What we're interested in seeing the change in the consumer surplus, the change in consumer surplus as we change policy. So for example, you reduce the registration tax of a car, well, that's going to make that price fall, and then you compare the consumer surplus before and the consumer surplus after, take the difference, and you see what is the change in consumer surplus after that price change. So these are the times of things you can calculate in counterfactuals. And then also now, if we want to talk about willingness to pay, let's consider a change in prices and attributes that holds the utility constant. This is what's going on right here, right? So you differentiate wherever that t appears. Let's move it. It should be j. Okay, there's no t's, no time here. So, well, okay. So what you do here is you consider a price change that holds the utility constant. Okay. So that is no, not only a price change, but in changing all the attributes. So I'm like totally differentiating here. Okay. And then I'm saying I want to have no change in utility. Okay. So no change in utility. Okay. And then basically I can calculate here basically the relative ratio between the change in the price and the change in that set. That should be set, the set j. That's a negative of the relative size of the coefficients, which measures the relative willingness to pay, okay, for an increase in set. So in other words, let's say set is something that we really like, right? We set is, you know, like leather seats in my car. Then and I, you know, I like leather seats. So and then we know we don't like price increases. So we think the coefficient on the price here is negative. You know, it's a normal good. So you don't like, you know, price increases. So this means that this marginal willingness to pay is going to be positive for the leather seats because the marginal utility of leather seats is positive. Okay, so we can calculate the things and measure how much am I willing to pay for leather seats by looking at the coefficient, or how much is the representative consumer or the average consumer willing to pay. So these are the kind of things you can calculate in conditional logit models or in discrete choice models more generally, except that then these you know, the expected utility the specific functional forms would be different, but you can calculate the same type of objects. Let's calculate elasticities here for the conditional logit as the last thing, and then we'll talk about substitution patterns in logit, just some restricted substitution patterns in logit in just a second, next video. So here's economists, they're often interested in measuring the response in terms of elasticities, since they are just normalized for the variable units, right? I mean, sometimes, you know, it'll be hard to calculate or compare the different marginal effects or partial effects across different variables, because you forgot what is measured in, you know, and what is measured in thousands and hundreds and so on, right? So that's why we often calculate basically elasticities. And if you do calculate those elasticities, so here's the elasticity is basically, you know, x divided by the probability times the probability times the derivative. Okay, so this is like you know, that's the definition of that elasticity. So it's an elasticity of with respect to a change in the attribute of alternative k on the response probability of alternative j. So k and j could be the same, but they can also be different. Okay, and then we have our derivatives from before. That's just repetition, and then we're just multiplying with that. This guy is that, and then you're left with this. Okay, so what you see here is yeah. So is of course the elasticity is going to be depending on the size of the explanatory variable or the attribute, and then the coefficient and the sign is solely determined by beta. One thing I want to, and then of course they have opposite signs depending on whether you are changing an attribute of the, you know, the good that you're looking at the market share for, or if you're looking at the effect of other goods. Okay, so depending on whether k is equal to j. Okay, so that's why you have this dummy here. Let's be specific and see. Okay, now here's the cross price elasticity. Okay, so this is what happens on the probability of alternative j if I'm changing alternative attributes of alternative k, and then j and k are different. Okay, now then this of course is going to be 0, and it collapses to this. Now what is striking here is there's nothing about essentially we see really that a change in an attribute of alternative k is completely independent of j. There's no j in here. Okay, and this means that this effect is basically the change for all goods other than k. It's the same proportional change. Okay, so and this is an implication of the functional form. This results come from Logit, okay? Because this is what you get when you differentiate the Logit formula and multiply with, you know, x divided by rho, or the derivative of a utility, yeah, yeah, okay, yeah, this is what you get in the Logit model with linear utility, okay? So we see here that a change in attribute for alternative k changes the demand for all other goods by the same percentage. Okay, there's no j on the right hand side. Remember, we're looking at the elasticity for the probability of alternative j, yet it has the same effect, and it does not depend on j at all. Okay, and so this is somehow called the independent. This is reflecting some of the substitution patterns imposed by Logit. Is called the independence of irrelevant alternatives. Okay, it's another way of seeing that independence of irrelevant alternatives, and we're going to look at many different ways of seeing it at that particular proportional substitution patterns implied by Logit in the next video. Okay, so let's take a little break.